Tracking the physical interactions of multiple charged particles in a vacuum involves a high volume of concurrent calculations. Every particle exerts a force on every other particle, requiring the summation of countless individual vectors. Relying on Coulomb forces and electric fields requires constant attention to 3D geometry. You have to map the magnitude and specific direction of every overlapping field to determine the movement of the system. Calculating the electrostatic potential replaces the forest of directional arrows with a single, continuous energy landscape. In this model, the directional arrows are consolidated into a scalar field. Electrostatic potential is defined as the work done by an external force to bring a unit positive charge from infinity to a specific point without acceleration. This relationship is expressed as V equals W over Q. The SI unit is the volt, where 1 volt represents 1 joule of work performed per coulomb of charge. By mapping space as a landscape of potential energy, the behavior of complex systems is determined by analyzing relative heights and depths, simplifying the reliance on 3D vector geometry. To build this map, we establish a reference. At an infinite distance from any charge, the electrostatic potential is defined as 0. This grid represents the zero potential baseline. Introducing a single positive point charge warps the surrounding space upward, creating a peak in the potential landscape. The height of this peak is calculated as Q over 4 pi epsilon naught times R, where R is the distance from the charge. Because potential is inversely proportional to the distance R, the height of the mountain decays as you move further from the center. A negative charge has the opposite effect. It pulls the grid downward, creating a deep inverted well in the landscape. This establishes a consistent sign rule. Positive charges generate positive potential peaks, while negative charges generate negative potential wells. To find the total potential at a specific point where these fields overlap, we look to the superposition principle. Because potential is a scalar quantity, overlapping fields do not collide as vectors would. The heights and depths add together algebraically to form a unified asymmetrical landscape. Total potential V at any point is the sum of the individual potentials at that specific ordinate. This allows for the calculation of complex systems using basic arithmetic addition of heights rather than trigonometric vector resolution. We can observe this interaction in the electric dipole, a system composed of 2 equal and opposite charges. The dipole moment, P, is the product of charge magnitude Q and fixed distance between centers, 2a. At a significant distance, potential is proportional to the dipole moment times the cosine of theta, divided by the distance squared. Unlike a single point charge, a dipole's potential depends on both the radial distance and the specific angle relative to the axis of the charges. Because the positive and negative charges are near each other, their fields partially cancel out at long distances. This leads to a faster decay of 1 over r squared compared to the 1 over r decay of a single charge. Along the axial line, the potential reaches its maximum absolute value because you are directly aligned with the charges. However, at the equator, the midpoint between the 2 charges, the landscape remains perfectly flat. Since the cosine of 90 degrees is 0, the positive and negative potentials neutralize each other along this plane, resulting in a potential of 0. Although a dipole has no net charge, its spatial separation creates a localized scalar landscape that decays rapidly as you move away from the source. This 3D landscape can be represented as a 2D map, similar to how a cartographer maps topographical terrain. These slices identify regions in space where the potential is identical, creating equipotential surfaces, shown here as contour rings. Because there is no potential difference along a single contour, moving a charge along an equipotential surface requires 0 work. These surfaces can never intersect. A single point in space cannot possess 2 different potential values simultaneously. If equipotentials represent the flat paths, the electric field represents the steepest path downhill. These field vectors always intersect equipotential surfaces at 90-degree angles. This length is defined by the gradient equation, E equals negative dV over dl. The electric field is the spatial derivative of the potential. Its magnitude corresponds to the steepness of the gradient, while the negative sign shows that the field points toward decreasing potential. We can apply this to a charged spherical shell. The potential increases as you approach the surface, but once inside, the potential remains constant at every point. Because the potential is constant inside the shell, its spatial derivative is zero. This explains why the electric field inside a hollow conductor remains zero. Knowing the scalar potential allows us to derive the electric field vectors simply by looking at the geometric slope of the map. Beyond identifying the landscape shape, we must account for the work required to assemble these charges in the first place. This requires a distinction between electrostatic potential, the energy per unit charge, and potential energy, U, which is the total energy stored in the physical system. In an empty universe, the first charge requires zero work to position. There is no pre-existing potential field to act against, so the total system energy is zero. Bringing in a second charge requires work because it must overcome the potential peak generated by the first. The potential energy of this system is calculated based on the product of the charges and their separation. Like charges result in a positive potential energy, while unlike charges result in a negative potential energy. For a system of 3 charges, the energy is the sum of the work required to place each charge relative to all others already present. The total potential energy of any configuration is equal to the algebraic sum of the energies of every unique pair of charges in the system. Mapping electrostatic potential provides a blueprint for the behavior of charges in space. By treating potential as a scalar landscape, we can calculate the electric field, identify equal potential boundaries, and determine the total energy state of a system without the complexity of traditional vector geometry.